right, we're talking torque again. Give me some examples that you said of torque, and we will attempt to see the things of force running at a lever arm and perpendicular. Yo, what to do?
The rotating door of a hotel.
The rotating door of a hotel. Okay. Now, this brings up an interesting point that we're going to see a little bit later on perspective. Okay. I'm not going to use it directly right now because I think there are some easier situations to see, but humor me with this. What perspective should you look at the rotating door in order to best see torque? Top-down view would be. So since that is the case, I'm going to ignore it for right now. It is a great example. It is a great example. I'm sorry. I apologize. Any others? Yes. Seesaw is a fantastic one. As a matter of fact, it's one I would have pulled out if you had not brought it up. Yes. Seesaw. Let's use seesaw to see. The saw and seeing of the saw. All right, here we go. We have seesaw. We have kid on seesaw. Nailed it. All right. Given this certain circumstance right here, what is definitely going to happen? This is a terrible seesaw, right? Why? He has no friends.
He's a lonely boy.
Or we can get very existential in this and kind of worry about his mental being. He is hypothetical. He has so many friends. He has all the best friends. Moving on. All right. Which way is he pushed? Down. So hopefully you can straight up visually see it. Okay. This force, of course, is being pressed down. Is there a lever arm? Well, let's start this. First thing we need to ask is, where is the fulcrum going to be? Okay. Okay. Fulcrum, remember, is the center of rotation. A couple of things real quick, just a gentle reminder. Where is the fulcrum of an object, all other things being equal, nothing else being decided? Center of mass is correct. Center of mass of an object. The only way that it moves, like in this particular case, is if something literally holds it at a spot, making sure that it rotates around that particular location, like obviously a hinge would in this particular case. So, answer me this. Is there a lever arm here? Yes, there is definitely a lever arm. Is that force? Let me draw it, by the way, because you are going to need to draw it. The lever arm on a picture is, by definition, from the fulcrum. So first thing you have to always do is identify the fulcrum. If you haven't, it doesn't work very well. The literal distance from the fulcrum to where the force is applied. There's your lever arm. There's R right there. Okay, we've already drawn force in this particular case. So third thing is the lever arm and force perpendicular in this? Sure, absolutely. So is the kid going to rotate? Let's talk sign of torques real quick. I know this is a bounce back to Tuesday, which everybody, no, I think everybody for the most part was in here. But gentle reminder, when is a torque positive versus negative?
Counterclockwise, clockwise.
So is this a positive or negative torque?
Negative.
This would be a negative torque here. Okay, and if you forgot how, here's what you do. Okay, let me just go ahead and overlay this. There's two ways to do this very quickly. Okay, my personal favorite way is to think of the fulcrum as the center of an XY axis. Then imagine your torque and see what direction and angle would be created by that torque alone. The direction, of course, it's going to go is here. And what kind of angle would that make? Positive or negative? That would make negative, and thus it is a negative torque. But again, somebody did already mention this, so let's go ahead and throw it up here as well. Again, counterclockwise, positive, clockwise, negative. And the reason I like mine is specifically, again, because we already know the way angle is positive. We're familiar with the way angle is positive and negative, and it's the exact same thing. Again, the reason we have to do this, why can't we just say up, down, left, right? As an object is rotating, all of those things are happening. This is currently going down, that's currently going up, this is currently also going left, this is currently also going right. Yes? And as you continue that process, that happens in a bunch of different ways. So up, down, left, right are not going to work for us. As a matter of fact, you'll see in just a second, when I put a second kid up there, why obviously this needs to happen in this way. That being said, what's now going to happen to the seesaw?
Yeah.
Seesaw is now going to what?
Negative.
Sure. Okay, so what's going to happen to it?
It's going to look like this.
It's going to tilt until when?
It's going to touch the ground.
Why does it stop when it hits the ground?
Because there's an equal and opposite force.
Oh, close.
It's a solid force. Can't go down.
You're very, very close by saying equal and opposite force.
There's balanced forces?
It's not balanced forces. Not because well, there actually is, but that's not what we're looking for. That's not why it stops.
Because
it's not because there's balanced
because
forces.
the Earth is there.
Listen to this carefully again. There's not because it's balanced forces.
Oh.
There are balanced torques. What happens when you hit the ground? What happens when you hit the ground? No. You're right with stop it. That's not what I'm looking for. What happens? Okay, what force? So watch here. Here, the kid was providing a torque. Interestingly, by the way, as the seesaw rotates, does the kid provide as much torque? No. Okay, why? Why does the kid stop providing as much torque? It's not perpendicular, so it'll be less and less as it continues, certainly. But when it hits the ground, right over here on the ground, okay, what's going to happen? Here's an interesting question for you. I didn't draw them quite correctly, so keep this in mind. Which should be bigger? See if you can't discuss this in your group. The force of the kid or the force of the ground pressing upwards? Discuss. Assuming, by the way, that they've bounced whatever and now they're just sitting there. Discuss quickly. Which one's bigger?
Force of the kid.
Kid is bigger. Why? Or I'll say that differently. Why is the force normal in this particular case smaller? It has more lever arm, and therefore to provide the exact same amount of torque does not require nearly as much force in this particular case. Notice also, this kid we said was what kind of torque? Negative. When they stop, this provides what kind of torque? Positive. Back the opposite way, countering in that particular way. Make sense? Okay. Transitioning into arguably something new. Everything today is building on torque, okay, adding some details out in all directions. We are not trying to go into too many more deep stuff than that. The main goal of today is just to see a bunch of different examples and torque in those particular spots. Let's talk about if you were annoyed with Spainhour for that last test. Not specifically about that test. We'll talk more about that tomorrow in ways that you can improve your grade and ways that will bounce you back and you'll learn in that particular process. Of course, I know full well that despite my old ranting and whatever, obviously you do care about grades, and I get that, so I want to make sure to provide systems that do both at the same time. You learn and get points back. We'll go with that. We'll talk more about that tomorrow when I think about that a little bit more carefully. Now, that being said, let's say you're annoyed at Spainhour for the test, so you want to bully him, right? You want to come up and you're going to shove Spainhour. Okay? There's a handful of ways we can do this, and let's discuss whether or not you are going to cause torque when you do that or not. Okay, so you come up to Spainhour, and Spainhour's standing like this, just looking off in the distance like an idiot. All right, and you stand up and you take your hands, you put them kind of awkwardly together. It's right in the center. Okay, and you come up and you shove them in the chest. What's Spainhour going to do? Go back. Will you provide a torque? Oh, think about what I'm going to do. Is that force that you did to push going to provide a torque? No. The answer is no. Why not? There's no lever. Where is my fulcrum going to be? Center of mass. And therefore, when you shove me, I will go back, I will accelerate, my forces will be unbalanced, but that force that you provided is not going to cause a torque. That being said, of course, some time passes by, and I got annoyed, I yell at you or whatever. Okay, and you found another time to come up and shove me, and I was standing looking off into the distance or looking outside, and so you walked up from this direction, okay, and you shoved my shoulder that way. Okay, now am I going to go that way?
Yeah.
Sure. Is it going to provide torque?
A small bit, yeah. It's lever on there,
There is lever on.
I don't think so because it would be parallel.
Correct. There is no torque provided that way. You would not expect me to rotate around in any particular way like this. Now, just as a heads up, if you're kind of being a little bit tricky here, just so we're very aware of where I'm looking versus where you're looking, okay, you might be thinking about me doing this, and I'm going to talk about balance a little bit later, rotating that way. That is certainly a piece as well that we're going to get into. But right now, we're looking at essentially, would you expect me to rotate like this, right? So here, okay, because I see kind of where you guys are thinking. So shoving here, again, is it going to make me rotate like that? No, because there was a force, but that force caused no torque in the first case because no lever. Now, again, keep thinking me rotating like this. Would you expect me to rotate like this if you came up and shoved me on the shoulder that way? No. Is there a lever arm? Yes, there is, because here's fulcrum, here's the distance over here. There is a lever arm, but there is no torque because the force of pushing parallel. If it helps, let us draw a picture here real quick. Okay, here was the first instance of Spainhour. Okay, here's his shoulders, totally not to scale or whatever. Here's his hands. Okay, whatever. In the first case, we shoved here and did not expect a torque because of this. Yes, fulcrum's right there. Next, still fulcrum. We shoved like this particular way. Would we expect a torque there? Absolutely not. So, humor me real quick. What would you do to cause Spainhour to rotate and torque? Does anybody want to provide an example?
I don't know how to do it. I would if I knew how to do it. I love pushing the spin
So, whichever side you want. Go ahead. Okay. Why does that cause a torque in that particular way? Okay, now it seems a little bit strange that she might come up, by the way, and probably not shove me, but obviously kind of like do that thing, just like a shoulder check right inside and hit somebody the opposite way, in that particular way, that would potentially do it as well. Now, let's say she really wanted to get into it, okay, so now she's going to use two hands, right? She just used one hand over here, then of course I would rotate, but now let's go ahead and hit me on both shoulders if you don't mind at the same time, okay? All right. Do both hands, you're fine, you can have a seat, okay? Do both hands provide a torque?
Yes.
Yes. Both hands do provide a torque. Did I rotate?
No.
Why not? Those are balanced torques. To counterbalance that with an example we had used earlier, let's go back to the very first example drawn up here, the kid on the playground, and put another kid on that slide. On the seesaw.
That's a bad.
Okay.
Hey.
It's fine.
These are way off the
All right. Obviously not drawing to scale. Bush, you've had bigger kids and smaller kids you've gone on the playground with. Yes, you guys know. How do you fix that? You got an older kid, a bigger kid. How do you fix the situation so that they can be on the seesaw together?
You put more kids on the skid.
Okay, but let's assume you only got the two kids. You got the older brother and the younger brother, and that's it. That's all you got.
You jump.
Come on, do this. Thank you. Who do you move closer?
Bigger kid.
You move the big kid, and hopefully now you actually have the understanding of why. Why do you move the bigger kid closer? Closer will do what? Will it change the kid's force? No. So what does it do? So it changes the amount of torque. Correct. Absolutely. That's what we're looking at in this particular case. All right, how are we doing right now? Got a bunch of examples. Let's look at another one. Let's look at a fun one. Difficult one. Whatever. All right, 6 of 1. All right. Imagine that you've got a hill. Put a ball on that hill. What do you expect the ball to do? Certainly you expect the ball to roll. Discuss quickly in your group in 30 seconds. Why does the ball roll? No. Don't miss this. Come on, do this stuff. Shh. This is difficult, and I've not heard a right answer yet, and you guys are treating it with not enough focus, because it's not an easy thing to see. The question is, ball's on a hill, it's going to roll. Agree with all of that. The question right now is why?
Because gravity's pulling it down, the friction pushing back the other way, so it's...
Discuss in your group, you've not given me a right answer.
Yeah.
Because it's perpendicular.
It's perpendicular.
That's always the answer.
But
So why is it
what do
rolling?
you think always answer?
The perpendicular. It's always freaking perpendicular.
Well, that's one of things that help it be the right answer. I will say if you just write perpendicular on a test, I'm probably not going to give you very many points. All right, I've got a whole thing I got to do here. Slow your roll. Discuss. We'll talk. All right.
I'm probably wrong.
I
All right. Firstly, I'll give a little bit of a bone to people that like want to get an answer real quick. Let me ask you a quick question, and then we'll step it back. Okay. Easy one first. How many forces are acting in this particular situation?
3.
It is 3. Which one of them is the only one and directly the only one that is responsible for that thing spinning? Friction is correct. Friction is the only one that is directly responsible. Let's talk about this and show you how you can analyze this. Not an easy situation, but I'm going to use this as a vehicle of discussing the next conversation. What we need to talk about now, and I promise we will come back right over here and finish this conversation, is a, I'm gonna put this in air quotes and hopefully not freak you out, a new type of force diagram. Okay, now, it's not meant to freak you out because it is the exact same as the old force diagram with one major difference. It's known now as an extended force diagram. Okay, in a force diagram, what was the rule about where you're supposed to draw all of the forces from? From the center. Correct. And the reason you're supposed to draw all of them from the center, which you did not know at the time, and now you do, is because if we draw all of the forces at the center, all things being considered, where's the fulcrum of every object going to be? At the center, and therefore, how much torque were all of the forces then causing prior to this chapter? None. We were not dealing with anything. As a matter of fact, another vocab word that you'll see on your homework is this. We were treating everything prior to this chapter as though it was a point mass, as though all of its mass was at a singular point and we could just move it around. When things went around in circles last chapter, like things in orbit, we didn't worry about the fact that technically some of its radius is smaller and some of its radius is further away. We just treated all of it as though it was in one location, right? When I walk from place to place, we don't worry about the fact that spanners front and spanners behind are not at the same location, etc. They're getting further apart. Okay, what we're dealing with is all of them at one particular location as he walks. That's known as a point mass. You can treat objects as a point mass and the corresponding use the force diagram if they are not rotating. If they're not rotating. If they are rotating, then we have to treat them as an extended mass, and as such, we need to do an extended force diagram. Here is the difference. An extended force diagram is the exact same as a force diagram. The only difference is you draw the forces where they're actually applied. Okay, so let me give you a for instance so you can see how this works and try to work it out. Okay, great news is if you're good at force diagrams, this is usually a relatively easy switch as long as you see it real quick. Let's begin with one of the easiest force diagrams you know of. A person is just standing there.
That's a weird stance, bro.
So isn't it very
Great, that's absolutely, it's a weird stance. It was just like, yeah. All right, moving on. Force diagram. He's all like, come at me, bro. All right. Let's go back to what would you have drawn prior to me saying anything today? Gravity down. And normal up. And that's it, yes? All right. Now here's the thing that's good, okay? And you'll see this again when things get more complicated in a second. When you draw the normal force diagram, ultimately nothing about that should change. Forces down and forces up should still be equal because while we're dealing with torques, the rules of Newton's laws have not gone away. Okay? All you are essentially going to do is take these forces and now apply them where they actually go. So let's talk about that for a half a second real quick. Where does gravity actually go? I'm taking my examples, I'm incepting out, I'm going one step further, we're coming back to this. Here we are over with the ruler right now, okay? This is the last time in this class I will be technical about this, and then we will just use the approximation from this point. Where is gravity on this ruler technically?
Everywhere.
Everywhere. It's all over the place. There's a stupid amount of arrows actually on here, but that would be incredibly difficult to use, yes? I think I shared with you, where is the approximation of where force of gravity should go on this? Let's talk about why. Okay, the reason is this. Okay, now that we've got a little bit into torque, now you can actually understand the reasoning for this. Well, imagine you're just dealing with this little guy right over here. Okay, does this guy right over here actually cause a torque on this system?
Yes.
Yes, it does. But if we are dealing with the center of mass, there is also a exact same amount of mass over here at the exact same distance on the other side. So what's true of their torques? They are, what is, yeah, right, okay, the balance is fine. Okay, and obviously we could do that all along the line. So how many torques are there actually? Well, as many arrows as you want to create, but what are they all going to inevitably do to each other? Balance each other out. So, where's force gravity actually technically? Everywhere. Where can we approximate it? In the center of mass. Why can we approximate it in the center of mass? What we're approximating is the location that all the gravities would counteract their torques, and as you're seeing right here, cause absolutely no rotation whatsoever. Does that make sense? So really what we're doing is not saying it's in the center of mass. We're saying it's at the spot where all the torques are balanced. We know that's going to occur at the center of mass. Does that make sense-ish? And by the way, it doesn't matter, of course, if it is symmetrical or if it is not symmetrical. If it is not symmetrical, for those anybody not here on Tuesday, I'm using the trick of using the 2 fingers, and all I'm trying to do is making sure the torques don't cause this to rotate. If I find the location, okay, that's the center of mass. That's where I can draw force of gravity. You know, why is it that this side gets a smaller lever arm than this side?
It's more force.
More force, and therefore to counterbalance the torques, it requires smaller lever arm so that the torques all count out to 0. Fair enough? All right. So in my extended force diagram, where does the force gravity go for a human? Anybody know roughly where the center of mass is for a human?
Doesn't it depend on like?
There's a lot that it depends on, but for the most part, there's a pretty accurate approximation of where it is. It is a little bit above your. It's a little bit above your belly button. Again, everyone's makeup is a little bit different, but for the most part, it's right above the belly button right here. We're gonna talk more about this a little bit later, but here we go, drawing the force diagram here. And remember, when we talk about these, we are dealing with, of course, the fundamental forces. There are 4 fundamental forces. The force of gravity is the attraction between all 2 masses. Between 2 masses. Electromagnetism is what? Attraction repulsion between electrons and protons. And the other 2 are strong and weak, but we never deal with those because they're in the nucleus until you come to the latter half of physics 2. My physics 2 class is dealing with it like right now. Okay, so going back to electromagnetism. Remember that if you do a force diagram, it's pretty much gravity and everything else is electromagnetism. When you remember that, you look up here and you go, actually, there's not 1 force normal. How many are there? There are 2 force normals. Where are they? On your foot. If you don't believe me, you can see this a little bit later. Spread your feet out, and you can actually feel as you slide back and forth from one foot to the other, you can feel the force normals distribute differently. Now, of course, if you stand relatively normal, what's true of both feet? Each of them have about half, and if you don't believe me, you can literally feel it, right? Pick up 1 foot, you will notice that you shift your center of mass, so it's standing directly above that foot, and now you can feel all the weight on 1 foot. Use 2, and now you have your 2 force normals. So all things being equal, where does force normal need to be drawn at? 1 on each foot. And roughly speaking, about half the size given this. But also you can kind of get an idea that it's not always half the size, right? If I stand like this, yes, we expect both feet to have about the same force normal. What happens to my feet's force normal as I shift this way? More gets this way, and also I have almost 0 over here. I can almost lift this one up because I'm not really using it at all in that particular case. Okay? We'll talk more about balance in just a second. But what I want you to see here in this picture is this. This is literally the same as this. All we did is kind of animation style, grab this and move it where it actually goes. Yes? So when it's easy, I think it's going to be easy. But when it's challenging like this one, I think people will screw this up. So let's start with this. Before we try to worry about an extended force diagram, let's just draw the normal one. I don't need you to do this, by the way, if you're doing your homework and you're like, yeah, I don't need to draw both of them, fine. But if you are struggling with the extended force diagram, feel free to do this technique. All right, what would the force diagram be on this ball if it was just a normal force diagram? Force of gravity down.
Normal up and right.
Okay, normal up and right. Oh, hold on. Thank you. Over here. Okay, normal up and right. And friction up and left, back up the hill. Yes. So like I said, if you struggle with where these things what this needs to look like, at least bare minimum start with what you know this is, because this doesn't change. You're not going to draw arrows in different directions at all. You are simply going to take these arrows and place them on the actual situation. Let's start with the easy one. Where does force of gravity need to go? Center of mass. So I take force of gravity. Come on, I'm doing the thing. I'm doing the thing on purpose here. and I move it where it needs to go. First question, based on this picture, you should now be able to find an easier thing. Where's the fulcrum, by the way, need to be on this ball? Center. So answer me this, because earlier somebody said some things that are not quite right. Okay, why is gravity not causing torque? It has no lever arm. Gravity has no lever arm. It is not causing torque in this case. That is both true and not true. We'll get to that a little bit later. But for right now, it's true. Next. All right, let's go to force normal. Force normal needs to be applied where? Well, it's electrons on electrons. So where's that going to occur? It's going to be right where it meets the slope, right? And if you remember, force normal gets pushed perpendicular to the slope. So let's go ahead and move this here where it needs to go. All right. Does force normal cause torque? No is correct. Does it have a lever arm? It does have a lever arm. Why does it not cause torque? Because it is parallel is correct. And friction, well, normal is electrons and electrons. This is just surface friction, so this is electrons and protons. Don't worry about direction, because again, we've already figured out what direction it needs to go. Where does this get applied?
Surface.
Exact same location as force normal, because it's the exact same thing. It's where the rubber meets the road, so I put it right over here, and we asked the question that I asked earlier, what force is it that's actually causing torque? Force friction is correct. And the reason why it's friction is because, does it have a lever arm? And to Haley's point, is it perpendicular? It is. You can't just like shake your head. There's like 7 other things that built up to this. You can't just, if you wrote, like, if I say what force is causing the torque in this case, and you just write perpendicular on your test, I don't think you're going to be happy with what the answer key actually says. But yeah, in this particular case, the ball is turning because of friction in this particular case. How are we doing?
Does that mean no more free body diagrams?
What's that?
Does that mean no more free body diagrams? I'm gonna tell you.
Excellent question. In this particular way on these, I would highly suggest no. I would highly suggest not on this case. You can technically get away from it, okay? Here's what you end up doing if you want to do a free body diagram. What you do is you draw a rigid object that represents the lever arm. So like if I was going to do this as a free body diagram, it can't entirely be free. You would draw something like this. Force gravity, force normal, force friction. And then you would put your fulcrum in that particular case, and then you could kind of see the same things I'm talking about right now. The nice thing about doing it that way is later on we're going to talk about things like ladders sitting on like the side of a building and stuff like that. You can kind of see the analogy in this particular case. But yeah. All right, let's move on. Let's take a quick aside real quick to kind of the math and all this sort of fun jazz real quick and hit some fun conversation on balance. All right. Let's actually go back to that picture I have over here on the right side, and everybody's like, you drew that super weird. I drew that actually very, very carefully so that you can see what it is that's coming next. Here's the truth about fulcrum, okay? I keep asking you, where is it, all things considered? You keep saying center of mass, and the truth of the matter is it gets super wonky because the truth is fulcrum, you actually get to place it wherever the heck you want. Now, in this particular example, what you might notice is this. No matter where I put my fulcrum in this particular setup, I will always find the ability to counterbalance one torque with the other. Meaning, watch here. If I put my fulcrum here, okay, positive or negative on that torque? Positive, because it'd be going this way. Positive or negative on that torque? Negative. And what's true of both lever arms? They're equal. And what's true of the size of both forces? So they are equal and opposite torques in that case. Now watch this. What if I move the fulcrum over here? A little bit weird, just on the left shoe, right shoe. Why the heck would you do that? Don't worry about that. Now, look at gravity. What type of torque does gravity now cause? Gravity now causes negative. Normal causes positive. They still counterbalance each other. To which you say, yeah, but gravity's bigger. Yes, it is, but what else do you notice? Gravity is bigger, so it should provide more torque from that, except because fulcrum is where it's at, it's got less lever arm, and actually gravity, we know in this case, is twice as big. And literally we know this lever arm is twice as big. So we've got equal and opposites in this particular case. So let's talk about balance. What does a person do to balance? In sports, there's a thing called athletic position. You spread your leg about shoulder width apart so that you don't rotate when someone tries to juke you out, that sort of thing. Terrible stance, of course, when playing shortstop or playing defense against somebody in basketball is this. I'm just going to stand like this. I hope everything goes well. Of course, if it gets hit over here to the right side, I'm probably going to fall over this way. I'm not going to be equally balanced to go both ways. Why is that? Well, if you do the diagram, here's what you're going to see happen. If a person starts to shift over here, and they shift too far, come on, stop it. And they shift too far, now we have force normal, probably smaller by the way. And now let's go ahead and say force of gravity is now out here. Now, no matter where you put your fulcrum, we have a problem. Watch. If I put my fulcrum, say, here, what type of torque is that going to cause? Actually, let's not get too mathematical. What is this person about to do if they went too far in front of their feet? But to fall on their face. In other words, they're going to rotate this way, right? We would say they're going to rotate in the positive direction. Yes? Okay, cool. Fulcrum's here. What kind of torque? What kind of torque? Positive. Do we stand a chance of counterbalancing any torques? You're going to rotate. What if instead of putting the fulcrum there, we put the fulcrum here? What kind of torque? What kind of torque? Do we stand any chance of counterbalancing? No. Now you could say, but Spanhauer, what about here? Okay, I hear you. Because actually this one is positive and this one is negative. Okay, all right. Except, which one of these two is going to be bigger? Which one of these two is going to have more lever arm? So which way are you definitely going to rotate? If your center of gravity gets outside, here it is real quick, just showing you physically right here. If I literally take my force normals and put them right next to each other, watch here, you can literally see it, or you can do it yourself later. If your center of mass gets outside of your force normals, that's when you start to fall over. That's when you start to rotate. So of course, athletic position is take your force normals and spread them further apart. Now I have a much wider range that I can stay balanced on, because I can provide the necessary torque to keep myself rotated. But once again, if I get beyond, I'm absolutely going to rotate in this way. This brings me up to, well, you guys aren't going to a bar very often, but one of a bar time bet that you can mess around with some of your friends. Watch this. If you go down to touch your toes, okay, thinking about what I just said, your center of gravity has to stay over top of where you apply force normal. Okay, watch carefully. If I reach down to touch my toes, what do all humans do in order to reach down and touch their toes? Right? And their center has to go forward. That would put my center of mass out this way. So what do? My butt sticks back. Yes? So here's the thing. You tell someone, you say, stand flat against the wall. Okay? Do the best you can to reach down and touch your toes without falling over. Are they going to be able to do that? Why not?
They can't add any counter
There's no such thing as a counter torque.
torque in the opposite direction.
No torque in the opposite direction.
Okay,
They can't.
Their center of mass is going to do what? Watch here. Notice the moment. The very moment I start rotating. I'm good. I'm good. Okay. When did I start rotating? The moment my center of mass got in front of the tip of my toe. So people with larger feet have an advantage on this, but proportionality works this way. They also are going to have more mass stuck out in front. Why can they not bend down and touch their toes? Their butt can't go back, which is exactly what you do when you reach down. Like literally look at what happens to my center of mass, which is like right here. Does it stay over top of my feet the entire time? Yes, and therefore I stay balanced in that particular way. Let's talk about another thing with center of mass. It's a little bit crass. We are going to be dealing with some gender stuff right here. We're just going to be dealing with it biologically in this particular front as well. Okay? If a male tends to put on weight, where do they tend to put on weight? They put it on in their stomach. And where did I say earlier the center of mass is? Pretty much in the stomach. So a male tends to put on more weight in the center of mass, where the center of mass is, so they can keep their center of mass pretty much in the exact same spots. Okay, cool, great, whatever. Where do females tend to take on more weight? They tend to take them on in the legs. And the reason why is because they have other biological things that males don't have. Right up in this particular area, we don't have to get specific with that. But due to that fact, as for example with pregnant women, which definitely happens naturally on that particular front, they tend to gain mass up here. And if they gain mass up here, they already have a hard enough time staying balanced as it is, because that does fluctuate. Even the sloths are not making it hard to balance. But as they gain mass up here, what would happen to their center of mass? That was it. The center of mass would go up. Even if they put mass on here, mostly here, their center of mass would go up, making it harder and harder to balance. So where would you put the mass so that it stays in about the exact same location? Well, if mass is going up here, then it also needs to be put in this area right here as well. Now, of course, if those things are roughly equal, then of course women do have a tendency of taking on in that particular. Now, due to this particular fact, every male and women of every varying size do have a different mass distribution. And if you have not heard this particular barroom bet, I'm excited to show it to you. I need someone identifying as a female to come up and represent themselves in a particular demonstration. It's not that hard. It's not that hard. You're going to look really good in this particular situation.
I'll do it.
Cool, come on up. All right. So I'm going to show everybody how to do this in case you want to try it later yourself. You don't believe me, you think I'm cheating, or I talked to Eva earlier about this, whatever. I'm going to have you stand against here. They're not going to be able to see your feet, so I'll show you what to do so they can see me. And you're facing that way.
Okay.
Facing that way. Okay. So it's okay. Now put one foot behind the other. Okay. Yep. And then do it one more time. Okay. And now mash your feet. I'll take that left foot and mash them together. Now bring it to the other. Okay. Now what you're gonna do is you're gonna lean forward and you're gonna put your head so it's about parallel with the wall. Okay. Okay. That's all I need. Okay. Just a little bit lower if you don't mind. Just a little bit lower so nobody thinks we're cheating. Okay. Can you put your head up against the wall, please? Now. Just lean to the wall. All right. Now grab the chair. Grab the chair and stand up with the chair. Oh, we're struggling here. All right. Interesting. All right. That's not too bad. Fair enough. Fair enough. Okay. Put it down. And we don't have that many dudes. Rock, paper, scissors, or I don't know how you want to tackle this. It's the two of you. Did you guys not notice this before? Lane is not here. Same thing.
Guys, I just woke up.
I've done this before. I know how this is gonna go.
Yeah, I know. It's fun anyway. All right. Feet against wall.
Mike, I also have Crocs on.
One behind.
Really far back.
Sure.
All right, again.
He's got
Okay, mash your feet together. Okay. All right, and head up against the wall. Yeah, you're gonna need to take your hands out of here.
You gotta bend down a little more.
Yeah, it's gotta be about parallel, a little bit more.
Yeah.
Can you get up now? All right, grab the chair. Okay, just go ahead and stand up. No, you lean back. Come on. You just like straighten out your torso. Straighten out your torso. Straighten out your torso. I know. And males can. It does not matter strength whatsoever. You could go to heavy weightlifters in the gym and do this exact same thing, and it works pretty much the exact same way. I think many people on TikTok actually have. So, same sort of distribution. Females have a little bit more weight on average in their legs, and thus they have kind of, if you want, a counterbalance that males don't have. Males tend to have more of the center of mass, of course, is at the belly button. Since the center of mass is at the belly button, that means at the hinge, more than half of their weight is above that particular hinge, making it harder in that particular case to counterbalance with this weight because it is smaller in that particular instance than females have in that particular case. All right. How are we doing? Doing okay? All right. Let's move on. Moving on. Sorry for people online. All right, going up to this. All right, I talked earlier about perspective. I wanted to talk a little bit more about perspective and how you know where to look. If you are struggling with how to do some of these homework assignments, I cannot tell you how many years there have been students that struggle with particular math and they go like, Spino, I don't know how to do this. And I look at their picture And I'm like, yeah, I don't know how you would have done it either. So let me show you how you're supposed to draw these. We saw this earlier with the seesaw example, but then also Spainhour being shoved example. Okay, in the seesaw example, we'd see it from the side. The reason that we see it from the side is what you really want to pay attention to is the axis of rotation is in and out of the board. Which way is the axis of rotation here? Right there, essentially, invisibly in that particular spot, rotating on either side of that. Where is, as we were dealing with Spainhour, and this speaks to exactly why you guys were kind of struggling with whether or not it would cause torque. We'll get to that in just a minute. Where was Spainhour's axis of rotation when we were dealing with him getting shoved earlier? Straight up and down, which is why top down is the best view in that particular case. Okay, let's do a couple more instances real quick. What if Spainhour, let's throwing this right here, of course, here are your axes right now to discuss. Y, X, and Z. Okay, again, real quick, that was Y, X, and Z. So which one of those did Spainhour just use to rotate like this? Y is correct. Okay, here's the axis that I'm rotating around. Okay, now if I got really frolicky or whatever and decided to start doing cartwheels this particular way, what would be my axis of rotation that you would draw from there? That would be Z. Z on that particular front. So obviously you would want to see that picture from this perspective in order to see the torques. What if instead I said, you know what, no, my kid does front rolls or somersaults or whatever the heck you want to call them, and I start somersaulting at you, which way would be the best axis of rotation for that? That would be X in that particular case. And like I said, when you draw this picture, the perspective you want to look at is whatever this axis is looking straight out of the board, right? Meaning, of course, for if I was doing cartwheels, you would just want to see dead on with the cartwheel. If you wanted to see me rotating like this, it's top down. And of course, if I was doing somersaults, you would not draw me coming at you. You would see me drawing somersaults. You would want to draw it from the side, just like this, okay? The reason I bring that up is there is a problem pretty quickly in the homework that deals with one of those like old school fantasy style like cranks on a well. You know roughly what I don't think you've probably seen them in person, but you probably know roughly what I'm talking about.
Yeah.
Okay. I'll show you real quickly how. I was also about to use that on the board. That's probably not a good idea. I'll show you how people like almost always draw it, and then they get themselves in trouble. They go, all right, well I think that's like it would be like this. You get this thing right here, and sticking out of the side would be a crank. Yeah, I have no idea whatsoever how you're going to see torques in that circumstance at all. On the other hand, the way you would want to draw that is from the axis. So as you are looking this way at the cylinder, the crank would come out like this, and you could either kind of do like a 3D thing here with the bar, or honestly, the easier thing would just be leave it like that and assume like the bar is kind of out in this case. This becomes easier to spot. Hey, where should you push that crank to get the most torque? Yeah, and in the position that I have it, what direction, either direction, should you push to get the most torque? So that's where you should press it. Which way should you press it to get the most torque? Either right or left, right? So like if you were going to go right, you would put a force like this, and your lever arm you can kind of see. Now you do that, of course, to say raise some bucket of water, right? Which would be from some string, and that string would tear off like right here, go right there. Which way would the string right here, which way would the string cause force on the cylinder? Down. Positive or negative torque? Negative. Positive or negative torque, which is why, of course, those would have to be equal so that you raise that thing up. That being said, you use a crank because while the torques are equal, what is not equal? The forces, because you have more.
And you're adding mass to the bucket.
More lever arm. What's that?
You're also adding mass to the bucket.
Sure, but that would create more tension, but you could get still less force out of that particular situation. We'll talk more about this tomorrow.
Are you gonna post